Hello, I'm Mr. Wilkinson, and this is Biologicool. Today we're going to be talking about water and the characteristics of water, the properties of water. You should have some kind of paper or notebook out and be taking notes with me as I go through this to help you remember this information. So today we're going to be talking about properties of water. You might be wondering, wait, didn't you say this was about biology? Why are we talking about water? Well, water is very important for all living things. Your cells are mostly made of water. In fact, most organisms have more water inside their cells than anything else. So we should have a good understanding about what water does and how it works in order to understand what's going on inside of our cells. So to begin this discussion of water, let's think about the chemical nature of water. So water is also called H2O, which means we have two hydrogen atoms and one oxygen atom. And if you look at them, they look like Mickey Mouse. Let's draw our Mickey Mouse here. Right there. There's our Mickey Mouse. We've got oxygen here in the middle, and the ears are hydrogen. Okay, we have oxygen and two hydrogen atoms. So oxygen and hydrogen are covalently bonded together, meaning they're sharing electrons. So sometimes the oxygen has that electron and sometimes the hydrogen has that electron. But oxygen tends to hog the electron a lot, which means the oxygen tends to be slightly, this is a lowercase delta, and it means slightly negative. And each of the hydrogens then don't get that electron, they end up being slightly positive. This means now that we have a positive end and a negative end on our water molecule, meaning that it is polar. Polar, having a positive and negative end. So we've got a positive and a negative end on our water molecules. And this is a very important property for water because it's going to determine all of the other properties that we're talking about today. They're all related back to this polar nature of water. So let's say we have a couple of water molecules. We need to draw them anew. So we're going to have a slightly negative end here and a slightly positive end over here. And we'll draw another water molecule just a little bit below that. So you can see here, this end is going to be slightly positive, slightly negative. Now, if you've ever played with magnets, you will know that a magnet has a positive end and a negative end. And when those two ends get together, they click, almost like magic. The positive is attracted to the negative end. And this is true even at the atomic level. The negative charge here is attracted to this positive charge. And that attraction creates a very special kind of bond called a hydrogen bond. Hydrogen bond. This hydrogen bond is just the interaction between these two polar molecules. So anytime you have two polar molecules that have a slightly positive and a slightly negative end, they're going to want to be next to each other. Now imagine you have a whole bunch of water all together. All of these water molecules are going to be sharing similar hydrogen bonds with each other. And that creates a special property. Because the water molecules want to be next to each other due to these hydrogen bonds, they are cohesive. They stick together. Water molecules want to stick with each other. You've seen this in nature. You see water droplets. They're all held together by these hydrogen bonds. You've seen water pooling up together if you've ever poured it out and spilled it anywhere. But not only does water want to stick to itself, it also wants to stick to other things, because these hydrogen bonds formed by the polar nature of water will cause it to interact with other molecules and want to stick with them, and that's called adhesion. So water is adhesive. Like adhesive tape, it wants to stick to other things. So water is polar, causing it to be cohesive and adhesive. Now what's interesting about both of these properties is that the cohesive nature and the adhesive nature of water can work together to cause water to go up against gravity. If you were to put water in a very small tube, maybe you've seen this if you have a very narrow straw, and you put a straw in water, the water level inside the straw will be higher than the water level outside of the straw. Scientists discovered that the smaller that tube goes, the higher the water can climb. This is how plants get water from the ground up to their leaves. They take advantage of the water wanting to stick to it and itself, and it will go up in these small tubes. These small tubes are called capillaries, named after our smallest blood vessels. And this particular phenomena is called capillary action. Capillary action. And what this means is if we have a small tube, we'll draw our small tube, and we'll draw a little vessel of water, and that tube will go into the water, and we'll draw our water line here, and inside the straw it will be higher. So this might be easier if we shade this in to see what's going on. There we go. So capillary action is when water moves up against gravity because of its cohesive and adhesive nature. Okay, moves against gravity. This should tell you that this hydrogen bonding interaction is a stronger bond than the force of gravity, because we can go against gravity to do it. Have you ever been at a swimming pool and jumped in and landed flat? Have you ever done a belly flop? If you have, you probably experienced quite a bit of pain. And that's because all of these water molecules at the surface of any kind of pool, we'll draw that pool, we've got all of these water molecules here, they're all sharing hydrogen bonds. This creates an entire network of hydrogen bonds that provides a very stiff and resistant layer at the top of the water called surface tension. If you want to get past this surface tension, you first have to break all of these hydrogen bonds on the top layer of the water. Some organisms are able to get around this property. They can not get and sink into the water. They can actually float on top of the water. These are called water striders, and you might have seen them in your local pond. One organism in particular is able to actually run across the water, a lizard called the basilisk lizard or the Jesus lizard, because they don't break these hydrogen bonds until they've already passed it. It's an interesting video to go watch if you want to look up how these organisms are able to do this. So all of these things, cohesion, adhesion, surface tension, capillary action, are all related back to the polar nature of water and the hydrogen bonds that they're sharing. But not only that, water takes a long time to heat up. We call that specific heat, high specific heat. And I'll draw a little thermometer here to help us remember high specific heat. That means that it takes a lot of energy for water to boil. Okay, so high specific heat means it takes a lot of energy for it to change the temperature of the water, which means also that water has a high boiling point. High boiling point or high vaporization. These are the same, aka boiling point is the same as vaporization. It takes a lot of energy in order to heat that water up. Maybe you've seen this if you've ever boiled water, right? You've got your pan and it takes a lot of heat here at the bottom to start boiling the water and creating some steam. That's why they say don't watch the kettle or it will never boil, which isn't true. You can actually sit and watch it and it won't take any longer. It just feels that way. So we've talked about a lot of different characteristics of water and the properties of water. We talked about how they're polar. Each molecule is like a tiny magnet, which causes them to create hydrogen bonds, meaning they want to stick with each other and stick with other things, which allows them to go up against gravity using capillary action. They can also create a thick layer that must be broken called surface tension, meaning that water doesn't want to really change its temperature and that it has a high boiling point. There's one more thing we have to talk about, and that is that water expands when it freezes. Water expands when it freezes. So if you've ever had a glass of water, ice water, you'll notice that the ice cubes are at the top of the water. They float on the water, and they're able to do that because when they freeze, they expand, becoming less dense than the water that they are around. All right, that's it for the properties of water. What I want you to do is take a moment and think about all these different characteristics of water, in particular this high specific heat, how much time it takes to change the temperature of water, and think about maintaining homeostasis, that you want to have that same state inside your body all the time. How does this high specific heat help you maintain that same state? Take a moment and write a paragraph about the properties of water and how they help living things.